Last night I recorded this video twice. First video, of course, the wife starts hollering for me. Second video ended up to be at least a 30-minute long, So, it was too long. Greetings and salutations, fellow YouTubians. My name's Terry Andrews Jr., also known as the J5 Guru. This is Wednesday, November 29th, 2022. I'm going to go ahead and get into this. I got a cheat sheet here and trying to keep an eye on the time. Got the timer running. Going to try to not make this any longer than it needs to be. Okay, Ramon did some more work. He changed out the belt. Basically, his theory is a lot of these parts can be purchased from Servo City off the shelf. I'm still kind of on the fence. This particular part cannot be purchased from Servo City, but this is a work in progress here. Pay no attention to that slot. I have no idea why he has it down that far. It's not physically possible. Yeah, so don't worry. We'll get it worked out. The one change he also made is he changed the diameter of the belts. I believe these the pulleys. I believe these are larger in diameter. Again, off the shelf, Servo City HTD timing belt. We also discovered that this particular profile, I believe it's a curvilinear profile, it's less strain on the individual teeth. So we're working on that. And then what he did here too, Servo City parts here, you can see the name and numbers pop up. That clamp down, this is converted to a hex shaft drive now. Ramon, what? We're using just regular old flat. We don't need a tapped hole. We don't want a tapped hole. We want power. We want strength. Anyhow. Also, the pulley itself has a, let me change transparency here if I can. Let me see, change transparency. Yeah, it is a hex drive. So while there is a set screw in there, it is a hex drive, broached hex drive. I'm warming up to this. I'm not 100% sold yet. We don't have the idler shaft and idler that isn't in here, again, from Servo City. It's off the shelf components. It's probably in this assembly but hidden somewhere over here. So okay, I'm at 250. All right, so that's kind of what's going on there. Still working on this monstrosity. Bear with us here. There's a lot of variables and there will be more iterations on this as we fine-tune things. Okay, so I'm going to go ahead and close this, and then I'm going to open up my version of the arm. I'd like to thank the Patreons, the Patreon members. You help tremendously with defraying some of the cost, such as this program, SolidWorks. This is a full-blown, full license SolidWorks. That I believe we have 2 available seats, if you will, or licenses, and I believe at least one of them is floating. And so this is a full-blown muy grande. We have to have it. We as the designers cannot use the maker version because we need the ability to have this little functionality here, which is the SolidWorks PDM, which gives us the ability to have all the files on a central server that we can pull different configurations, and all the files are synced together, and I can work in my own kind of sandbox, and Ramon can work in his, and then we can migrate it over to the main server in the main CAD. There's a lot of things there. So this is full-blown legit, and you Patreon members help defray the cost of SolidWorks. And if you ever looked into owning an actual version, professional version. That's what this is. I'm not, let me see here. Here we go. About SolidWorks. Yeah, not going to show you the serial number, but yep. Professional 20, yep, service pack 4, fully legit here. So, okay, I'm at 5 minutes. I'm all, yep, okay, so. First of all, I'd like to thank Kyle, yeah, for the finger servos. I realized in my earlier iterations that they were too wide and they were too high. And after talking to our teammate Kyle, he had done some prototyping on his own based upon my prototype design, or maybe he come up with some flavor of his own. And basically, what I had done is I had put the pulley on top of this horn. That made the servo way too high to be able to go under these arm coverings. He said, hey, I ran mine down here, my cabling. He said, that works fine. It works perfect, not a problem. So we got to dot the I's, cross the T's. Of course, this particular screw here, this is a vented screw, which is an off-the-shelf part. It's used in industry. It's available through MIG Car. And that's where, so the cable sheath OD diameter fits within this socket, okay, and then is held captive in there by the fact that it will hit this surface. The inner cable itself that does the actual transmission of power is it's a thin cable. I think it's 24 thousandths solid steel cable. I forget the exact strength rating of it, but it's actually quite high, considering it's just moving the digits around. There are 3 of them in here. Again, we're iterating. This is not in the exact, at the exact angle it needs to be. That needs to be moved. This is above my particular SolidWorks pay grade. I will, go to Ramon and say, yeah, he does the hard work. I come up with the baseline designs. He pretties them up, and then we do devil's advocate. He says, what if we do this? What if we do that? And I go, yep, we can do that. We can do that. No, we can't do that. It takes away from the structure or the strength or interferes with this, that, or the other thing. And that's the basic way we go about doing that. I had to think fourth dimensionally here.
It's perfect. You're just not thinking fourth dimensionally.
Right. I have a real problem with that.
In order to get all these servos to fit underneath the coverings, okay, they do all fit. They are at different relative heights to each other, which means like the finger cables are very, the outer sheathing and the cable itself is very thin, so it's very flexible. It can kind of wrap past certain things. You'll notice this structure down here. This will need to be, obviously there's an interference there, or would be if there's a cable coming out. We will go ahead and we'll address that by kind of shelling out the area that we need to, not shelling, but, removing material that doesn't need to be there, and still allows it to be easily assembled and disassembled. Okay, so I'm moving on to the elbow servos now. Elbow servos, they're not elbow servos, they're wrist servos. Okay, so wrist servos. First of all, I want to touch on what all these servos are. All of these servos are, and I have the page pulled up here. These are sold by Servo City. They're 2000 series dual mode 25-2 torque versions. Okay, the SKU number on that, you'll see it there, is 2000-0025-002. That is the build system of Go Build servos. These are rated for 350 ounce inches at stall. Okay, these can run on a voltage anywhere from 4.8 volts all the way up to 7.4. We will be running them at 7.4 volts. You get the maximum amount of torque at that voltage. You're running it at the maximum it can do. It's a dual mode servo, so it can be programmed to run as continuous rotation, or in our case, as we needed to do, as a servo itself. that particular configuration gives you 300 degrees of maximum rotation, and that is the default as it is shipped. Okay, so let me see here. Oh yeah, price. Okay, you can't afford not to buy and use these servos. Okay, these are $31.99 a piece. Okay, buy.
Cha-ching, cha-ching.
Okay, don't buy just what you need. Buy what you need and plan. Yep, you're going to be buying spares. Okay, these things won't last forever. They may not be available forever. There may be a design change which makes it so it doesn't work in the arm with the components you have that have already been designed. Okay, I can't stress this enough. Don't wait for the manufacturer to just one day say we phased this version of the servo out. It has happened so many times over the years, I can't begin to even start, tell you how many times. So, okay, each one of these servos has a housing here. Okay, this is a 3D printed construct. I'll change transparency. You can see again we have vent screws. These are larger to accept the larger diameter sheathing and pull cable that goes through here. Okay, again, McMaster car. We have square nuts on here, and there will be a hex screw just like with the finger servos. This is your method of tensioning here. This is how you get the slack out of the cable system that goes to either the wrist rotation or the wrist up and down. Okay. So on one of these, what I opted to do is to make both of these the same exact diameter, the same exact part. So this way, when we go and have these made, we don't have an increased cost by making two different parts. We use the same part. This is a substantial, well, not to, it's 0.6. These are 1.5 inches in diameter, as to where these servos or these pulleys out here are, I believe, what is it? Oh, geez, memory's failing me. It is, yeah, 2.2, yeah, 2.25 inches in diameter out here. So if I've done my math correctly, which I don't know if I did, but basically these smaller pulleys give us an increase of 0.6 gained in the ratio. Okay, so that means what we've done here and what I specified is, since this is a 300-degree rotation servo, I want a buffer on either side of that maximum rotation, just to take into account maybe servo issue, yeah. So we've done this pulley diameter so that it is it uses a maximum of 280 degrees of rotation. With that, you can get 180 degrees of rotation out of this plate right here. Okay, that's the maximum J5 specified travel for that particular articulation. Okay, this pulley down here has a slightly lower rotation, which is 160 degrees. Okay, so I've already spec'd out basically the on-screen travel times, or what I believed was a good fast travel time for these servos under no load. You can see wrist up and down should move 160 degrees in 1 second. Wrist roll 180 degrees in 1.53 seconds. Forearm 154 degrees in 1.3 seconds. We meet or exceed all of these. Okay. Let me see here. I'm referring back to my cheat sheet here, folks. Bear with me. Okay, so we get an actual increase in torque down here. The servos are spec'd out at a maximum stall torque of 350 ounce-inches, if my math is correct, with this particular ratio, with the pulleys or the driving gear driving pulleys being smaller than the driven pulleys. That should equate to 560 ounce inches. So an additional 210 ounce inches of torque by simply, doing a ratio here instead of a 1-to-1. Not to mention the fact in this configuration, it's impossible to fit a 2.25 inch diameter pulley in here without it going through the cover or the inner arm. Okay, let me see. One thing I'll hit on here that's actually towards the end of my list. So when you look at these plates will have holes for these servos to go through, okay? And there will be an internal skeletonized 3D printed core, okay? It will have what it needs and nothing it doesn't need. So there will be portions in here that are for strength. There will be portions in here like a thin wall feature that prevents the timing belts from vibrating and the teeth rubbing against each other. Or, like here where it's real close to the servo, there'll be something up here and down here that prevents that belt from rubbing on the side of the servo. All of these servos are done in a manner. This is the mechanical side, this side. There are no electronics on this side. Spinning, whirring things, cables moving around, that might be flexing under load. Yeah, you don't want them anywhere near any of the wiring, okay? So, when you're working on the robot, if it's a mechanical issue, you got a cable issue, whatever, servos acting up, you work from this side. Those servos pull out from this side, okay? So they go from here and they go straight out, okay? They will be held in here by a couple of tabs with screw holes, okay? The other thing I might mention is with these particular designs, no forces of the elbow articulation or fingers are imparted into the arm frame itself. It is all self-contained within the servo assembly, okay? So it's not like you have screws going down through into something else where that has to absorb that torque. No, these are actual assemblies that operate independently. That also means that when you are adjusting cable lengths and things like that, they can actually be outside of the arm. Their operation and functionality is not dependent upon being inside the arm. That's one of the things I try to do is, things have to be, you have to be able to maintain it. You have to be able to put it together, take it apart, and maintain the thing, and things like that. This side over here will be entirely electronics. That particular plate is hidden, but everything from basically this point here on down, you can load up with your electronics, okay? One of the things that will need to go in that area will be the servo amp board, which drives the ASME servo for the elbow drive, okay? Then you'll be able to have your power distribution. All of your servo wires will come out to this side. There will be no servo wires which are on this side, okay, the mechanical side. They will all go through the core, through the other plate, and then terminate in some manner on this side. So again, if you need to work on the electronics, you pop off this side covering and all of your electronics are maintained there. Also, the provision is there. If you do not want to use this particular potentiometer, there is enough room to mate place an actual potentiometer on the drive, the point of articulation. Hey, shits and giggles. So, let me see. Okay, looking at my cheat sheet again. Wiring, mentioned that. Mechs separated, mentioned that. Core, mentioned that. Servos pull out, good. No forces imparted on the arm structure, yep, covered that. Torque values, yep. Okay. Belt size in this current one has been changed. Ramon's new design uses a 9mm wide belt as to where this one uses a 15mm wide belt. We've ran the numbers. It looks like a steel cord belt has more than enough, it will be more than strong enough. Again, this is kind of one of those things where we're still spitballing. I'm personally running through all the various calculations and, inside my head, and, what skookum, what sucks, basically when I do a design like this, I do the design to be bulletproof. And then at the end of the things, I'm like, okay, it looks like everything works. Okay, where's the weakest point? What's going to break first? And in a particular iteration I come up with, I was like, okay, well, there's 2 set screws in here because there's a D shaft and the pulley has a round hole. We have the same basic consideration up here at the drive pulley, where it is just a straight through hole where there's 1 set screw for the drive, into the D shaft. And I say, okay, if it's going to fail, it's going to be, it's going to become loose or whatever because of that set screw. So I do kind of like Ramon's idea with the hex drive here. I'm warming up to this end. I think we may do it his way here. But I'm still working on, I kind of like what he's done. I just have to make sure what he's done and what I'm doing with these, servos, that it all works. It's got to fit at the end of the day. Also, the plates will be they'll be mirrored. Basically, they'll be identical parts when we go to have them fabricated. So you'll notice over here that there are 4 holes that seem to be doing nothing. That's because over on this plate, they actually are the holes used to hold the ASME servo on. So we're going to try as much as possible to do that exact thing. So we're only having 1 plate, 1 design laser cut. And again, that keeps down costs for everybody. So instead of 2 separate panel designs, which cost more money, we go to the, the fabricator and say, make us X amount of this plate, of this single plate. And then when you get the plate, the holes will already be there. But if there's any countersinking, like down here on these arm plates, same basic thing, you're going to go ahead, and for this side plate, you countersink this side. For this side plate, you countersink the other side. Rinse and repeat. Same thing here. Countersinks here on this plate, the opposite side. So that way, when you get your plates, they are either left or right. If you buy extras, just to ensure that you have something for longevity, in case something bends or breaks by the off chance that you do something incredibly stupid or your robot takes a tumble, you just get into your parts bin, pull out a blank of one of these, and then do the countersink modifications, and you're golden. You're back up and running in virtually no time, instead of saying, oh gee, I have 3 right plates but no left plates. And we're doing the same thing with the arm core. So I know this is a lot to take in. I know I'm swirling around here like a little ballerina with this CAD, but I didn't want to make this video too darn long. But I did want to make sure to hit on all these points that I, missed in the last 2 videos I recorded. So I think I've covered everything. I'd like to thank all of my team members. I mean, everybody has contributed something to the design. I have talked to like Dave Stapley and over in the UK, Kyle Dadona. God, I think I butchered his last name again. Sorry, Kyle, dude. You're going to have to say it phonetically for me, and I'm going to have it record it, and then just keep listening to it over and over until my tongue-twisted pronunciation of your name is correct. But yeah, they have prototyped a lot of this stuff, and said, hey, I found this works. I found this doesn't work. I found when you do it, when you put the belt on the outside of the arm, it's problematic. The belt's in the way, and it imparts a weird torque force on the side plate. So this is not a 1 or a 2-man show. This is a collaborative effort between just super bright individuals on the team. And that's kind of the key to the success of this project. I surround myself with intelligent people that know how to get things done, and are not afraid to say to me, yeah, that's nice, Terry, but I don't like it. Or I have a better way of doing it. And I say, hey, Kyle, can I steal your idea? And he'd be like, yeah, go, feel free to, because he's already tested a very, a version of it that he says, yes, it works. Now, I will say, and I actually didn't write this down, these finger servos, yeah, the amount of torque that you're going to be able to generate on that pulley cable to move these fingers is enormous. As a matter of fact, I think it will exceed the braking strength of the high strength finger cabling. If you 3D print the fingers, it will be able to break the fingers. So, builder beware. I've always said, I want this thing to, I want the hand to be able to crush bone, and I want the arm to be able to pick up and carry me at least a beer, and in a perfect world, if the arm isn't fully extended, this thing be able to grab me a 6-pack and bring it over to me.
It's Miller time!
What's the use of having a Johnny 5 robot if all it's good for is doing nothing except for looking pretty and moving around? Yeah, it's got to be able to do at least one thing, And so if it can bring me an adult beverage every once in a while, I'm cool with that. I don't know what the programming of such a system like that would entail, but it would be pretty cool. So there we go, folks. Again, sorry, video went much longer than I wanted. I was trying to keep this to like 15, 20 minutes. I see I'm at 27 minutes now. So that's it. We are working on this. There are so many variables. I can't begin to tell you. When me and Ramon and in the past, Andrew have started CADing, they are doing the real world, in CAD world work, and inside my head, I have my own version of the CAD where it is bouncing back and forth. Will this part hold the torque? Where are the forces going? All of these different things. It seems to be kind of my gift, if you will, being able to mechanically analyze all of these different interacting parts and structures and being able to make it work. And so far, I think I've been pretty successful. And I asked like Dave Stapley, I said, hey, what is it about the robot that you don't like or doesn't work well? And one of the things he said was the tool arm covering. He said it doesn't have enough rigidity. Now I do know, I believe Andrew designed that, and he designed it, to his credit, pretty much identical to the original one. But again, my personal experience, I worked on the original tool arm covering was a floppy piece of plastic. It had no rigidity. So basically what Dave's saying is, hey, when I got this thing out and I'm moving it around, that whole thing is rocking and rolling, and it doesn't want to stay together. It doesn't have any really good points of fixation. And I'm like, okay, that's on my to-do list. We'll add in some ribbing in there, some structure, some metal components where, tabs and screw holes where you can screw it together firmly and things like that. But other than that, he really said he hasn't run into any problems, and I believe Kyle was about the same thing. And when these guys prototype this stuff, and build it, and they come up with a problem, I say, okay, I'll fix it. I'll give you a workaround, and I'll try to do something that is not a completely new design if possible, but something that is a retrofit, so they don't have to go and throw away all of their parts because, all of their like side plates or whatever, because the new design is just so different that they can't use parts they already have, that they paid for or made, so yeah. Okay, so approaching a half an hour. We're done, folks. Again, thank you Patreon members, thank you YouTube members, thank you Facebook members. I am back. I am off of my hiatus. Yeah, good things are coming, and yeah, I'm hoping to within the next I don't know, few weeks. Me and Ramon only have Sundays to work. It's just our schedule now. We got time that we block out on Sundays, and I work on it during the week on in my sandbox. He works on it in his sandbox, and then on Sunday we go, okay, let's do a Vulcan mind meld. Best of both worlds, you know. Let's get her done. So I'm hoping a few more weeks, a month, we'll have a finalized, non-tested design. There's that caveat, not tested. Works in CAD world, does it work in the real world? Well, that's where, pro builders, if they're feeling froggy, they can go ahead and build the prototype version. No guarantees. We might have to go back and make a major revision based upon the fact that you guys come back and say, yeah, it works in CAD world. In the real world, it kind of sucks. One thing I did miss. The cables. Cables will all go into a hole in the side of this plate and will run internally. Okay? And there will be structure in there so that those cables cannot hit the timing belt. Okay. And then there will be a slit, from that slot going to the outside. So when you go to disassemble this, you don't have to worry about the cables being caught in the side plate. The side plate will have a provision for those cables to slip right out. This way, when you're assembling and disassembling, it's pretty much a piece of piss. Not a problem at all. All right, there we go. 32 minutes almost. Okay, well, bye.